introduction. Okay, yeah, so yeah, so this is the slides for the self introduction. Sorry. I was born a while ago. So and later and right now currently I'm a postdoc in the University of Chicago. So working on quantum information theory. So in the past I have a background in physics and in quantum physics in Caltech as a PhD. So this is a very short, introduction, a word line of myself. So and today the topic, so I will discuss is a so-called quantum AI or quantum artificial intelligence, or more precisely quantum machine learning from a near term to fault tolerance. So that is a title. And then currently I'm supported by University of Chicago and IBM, and also two other startups and so-called Kubernetes and Secure. So those organizations are funding my research. So that is so maybe we can start from that. So this talk was based on my previous work and some of my previous work above, and also some work in progress, and together with collaborators, including my primary advisor in my postdoc, Lian Jian, and also together with other faculties and students. Yeah, so maybe I can give a brief introduction about things so I am interested in. So I'm primarily interested in so-called physics of data science. So at the moment, where I was trying to understand, so what is the basic principle of data science and machine learning? So how to design those algorithms, and is there any like a basic principle about designing algorithms? So using physics way to understand the underlying principle of data science and machine learning. So this picture summarizing some of my work and together with different people. So where today primarily I will talk about these two works, where the first one is so-called QNDK series, so quantum neurotechnic kernel, and which is QNTK for short, and about near-term quantum computing using variational algorithms to run machine learning type experiment, and also a so-called HHL algorithm, which is working in in the time of full tolerance of quantum computation. So I will primarily talk about these two topics today, but I'm happy to also discuss other research directions and also projects I have. So this is a brief introduction about my interest. And this is a simple outline of the talk that today I will give, so which is very simple. So the talk was roughly split into two parts, one for the near term, another one for tolerance. Where in the first part, I will briefly introduce what is the theory of quantum neurotechnic kernel, QNTK, so which will provide a basic analytic principle of designing and variational assets and variational quantum algorithms in the NISQ regime. And also I will also point out another ongoing work later about some application of large-scale HHL algorithm in the fault-tolerant quantum computing for machine learning, and providing. I will show that those algorithms will provide some benefits about for quantum machine learning running quantum machine learning algorithms in the quantum devices. And finally, I will give some comments about those algorithms. And then at the beginning, I will give a brief introduction overall and for curious audience. So that's a basic outline of the talk. So maybe we could start. So in the middle, so at any time, feel free to interrupt me in the middle if you have any questions, or you can ask me later if you want. Okay, so let's start. And firstly, I will give a brief introduction of quantum machine learning and to make a summary about this area. So quantum machine learning is an area that is in a very active development. So by definition, it was combining machine learning and quantum computing, which are two very promising technologies of the world. And people are curious about combining those two hot topics together and see how it will come, and it seems to be very interesting. On the other hand, so at the moment, so maybe we will already say that there are some benefits for combining those two together. And for instance, machine learning in the large scale might be very like costly, and we will be curious about how quantum computing could improve them, or going another way. So we are curious about how machine learning could help us to understand quantum algorithms and also quantum devices. So it's a very active area at the moment. There are also some very big picture problems that people are trying to understand. And also those are the part of the motivation that about some of my works that I will talk today. So firstly, what is the definition of quantum machine learning? So by definition, it was running machine learning type algorithms in the quantum devices. I will use this kind of definition, but can we make it to be more precise? Is there any like generic procedure about quantum machine learning algorithms? So furthermore, so why we use quantum machine learning and where is the quantum advantage? So why we don't use classical machine learning instead, or what's the difference between quantum and classical? And also, what are the successful examples or typical problems for quantum machine learning we need to solve? And also, if we are going to do supervised learning, so what is the quantum database? Is this database quantum or classical? So basically, we're asking, are we using quantum data or classical data for quantum machine learning? And is there any difference? And finally, what are the most successful quantum machine learning algorithms? So what is the algorithm that are most successful and could potentially be the killer application? Of them does not have a definite answer at the moment. Where many of the work, including my works, are trying to understand in some degree part of those questions. So furthermore, so development of quantum machine learning must be aligned with the development of quantum algorithms and the quantum hardware. So we know that currently we are in the NISQ area where people are able to control a few qubits, some number of qubits, which could be potentially large. However, quantum noises will limit the implementation of quantum circuits in a large scale. So in order to, perform more accurate computation, we have to do quantum error correction. However, it is challenging at the moment to build for the large scale fault tolerant quantum computing. So we might still have a few years from NISQ to fault tolerance. And then we are curious about how quantum machine learning will be like a setting in those two era, and what is their role. And especially how those noises and appearing in quantum devices will affect some quantum machine learning problems. So those are also the questions we also want to solve. In the next era, we already want some like successful applications of quantum machine learning, maybe for specific problems. And in the long term, if we have a very good quantum machine, we will be very curious about how they could help quantum machine learning. So those are the some underlying backgrounds about my talk. So that's why my talk today was split in two parts, where I will discuss and how quantum machine learning algorithms could be related to those two different computational eras. So so if there is no further questions, I will start. And firstly, talk about my theory, so-called quantum neurotiny kernel in the NISQ era. and later about HHL algorithm and how we could use it in the fault tolerance era. So feel free to ask me questions in the middle. Yeah, okay, let's start. So about the NISQ era, so often people are talking about so-called variational quantum algorithms, VQA. It's also sometimes called quantum neural networks or variational quantum circuits. So the idea is that so we could have a programmable version of the unitary and which could be made in some relatively shallow gates, so shallow quantum circuits. And for instance, here is an example where we have some local rotations, Ry, and parameterized by some classical variables, theta, and come together with some other gates. Like here it is a few C naughts and introducing some entanglement. And we could have multiple layer of them from this small l equals to 1 to capital L. And this notation stands for some generic form of those variational algorithms, and where WL is non-trainable gates, where together with e to the I theta x, where theta is a classical variable and x are some Hermitian operators like local polys in this figure. So this is called the variational quantum circuits if L is not very large. So in this case, we are able to program this kind of circuits by changing different variables of theta. We could even make a loss function and try to perform some classical optimization methods with respect to theta. With respect to this unitary. And for instance, we could make it to be acting on some states and try to minimize the expectation value over some operators. So that is our loss function. And we could use classical optimization method, or for instance, gradient descent algorithms, try to minimize the loss function. Because the variable theta is classical, so we are able to use classical method, to train them, but the loss function itself is made quantumly by quantum measurement in the quantum devices. So those kind of algorithms and are also some called the hybrid quantum classical algorithms, or we will say it's a variational quantum algorithms for short. So this kind of algorithm are successful, and people claim that might be used in the NISQ era because some of the applications we have in mind might be not that sensitive about the noise and precision. And for instance, in some classical machine learning problem at a large scale, and we actually don't need to do very accurate computation. So in that case, maybe we are able to already using those devices, even if it is noisy. So that is the basic idea. And I will talk about this briefly later about its theoretical foundation. So an example of this kind of application is variational quantum eigensolver, so-called VQE, and also NISQ quantum computational chemistry. And also, if we are going to do supervised learning, it's going to be quantum neural networks, and we could apply it for some machine learning problems. So that's kind of why people call this architecture also quantum neural network for quantum machine learning. So however, although people are trying to apply those algorithms in practice and receive some results and get some results for running those devices numerically and experimentally, but there is lots of confusions about this kind of algorithms. So firstly, why might it work? So why this architecture was something interesting that people want to study? And also when it cannot work. So those are like generic questions, and people already find some partial answers, like so-called barren plateau, and which tells us sometimes that this kind of architecture actually does not work. But people still does not know that much about the general principle about why people are using it, how they could outperform classical, and also what's the difference between this kind of neural network to traditional classical neural networks. But people are still trying, and it seems to be interesting, but there are still lots of theoretical foundations that are missing. So some generic questions in theory is that how to firstly choose the variational assets. And just now I already showed this is an example of the variational circuit, but they are designed by local Ys. The question is why you choose local Ys instead of local Zs, or some other combination of C naughts. So all of them are possible. So if we have two choices about this architecture, which one is better? So this is a question. And secondly, how good the convergence will be, at least in some limit, if we are going to use some classical optimization algorithms, especially gradient descent algorithms, how to converge. And also, what does the gradient descent dynamics look like, how it will train and during a different number of iterations. And also, as I mentioned before, what is the difference between quantum and classical? So these are like generic questions about variational quantum algorithms, where my theory of quantum neural tiny kernel, I hope will answer some of those questions. Okay, let's start. So right now we will see some formulas, and I will explain them a little bit. So as a warm up towards the full theory of quantum neural tiny kernel, I will show you a simple VQE or optimization example, and later extend to general supervised learning. So we are starting from some states which is parameterized by those variational angle theta and this unitary acting, which was discussed before, acting on some computational basis states, which are sufficiently simple states. And then using it, we could make a loss function, where here I'm specifically talking about the quadratic loss, where we are using the difference between the prediction of its expectation value over some operator O, and minus its some constant O0, which could be arbitrary in principle in this case, or you can even set it to 0 if you are going to minimize for instance, the eigenvalue of the operator O and find its ground states and its eigenvalue of the operator O, like the Hamiltonian. You could set this number to 0, but in general, I just keep a constant here for future convenience. I will call this whole quantity, which is epsilon, so-called the receiver training error. So this is a term for linear regression, but which is basically the difference between the prediction and the answer. And which is here, it's like a prediction is here, which is the expectation value minus the constant. So this is the definition of the loss function. And this fancy D, and in this equation, was the difference between for a variable between the two different time steps. So this is basically the definition of a gradient descent, and it was equal to minus eta, where eta is so-called learning rate, a constant, a small positive constant, times the derivative of the loss function over the variational angle. So that is the definition of the gradient descent algorithms. So, and then you can use some other algorithms, but today, primarily in this talk, I was studying this gradient descent algorithm. And this is just a definition of the algorithm that tell us how to update and train the classical variable theta L. So the point of my theory, quantum neural tangent kernel, is that instead of studying the variational angle theta, so let's study the receiver training error epsilon instead. So which is the change of the receiver training error between two time steps, adjacent time steps t plus 1 minus t. And in the limit where those quantity goes small, we are able to use the Taylor expansion, where we are doing the first order Taylor expansion, which is taking a single derivative times the change of the variational angle, and which is already defined in the algorithm. And in this case of the quadratic loss, which is one of the most common loss and people use in machine learning, and then after a few algebra, we will say that this quantity was equal to minus eta times a bunch of a quantity, and which is a non-negative number, where here I call it k, so-called quantum neural tiny kernel, and the times epsilon itself. So this is basically, of course, almost the definitions with a few line of analysis. But we will immediately notice that if this quantity, and which is the sum over variation angle and L, and of the square of a single derivative of a residual training error over the variational angle, this quantity, so-called quantum neural tiny kernel, if this is a constant, then you could immediately lead to an exponentially decaying solution of the residual training error and also the loss. And for instance, you can imagine this as a ODE, and in your ODE class, and probably this is one of the first ODE you have learned if you understand this fancy B as the time derivative, and then a first order time derivative of the object is equal to minus a constant times the object itself. And the answer will be an exponential decay solution, which is one of our most favorite solutions, and it's exponentially decaying an error, which means it's a good prediction. And in this case, where it is a finite difference case instead of the actual derivatives, we are able to directly get a closed form solution as well, which is also exponential decay, which is also a few lines of analysis to verify it's true. That in the case where k is a constant, the solution is that of the losses 1 minus eta k to the t, however, and times the residual training error epsilon at the beginning. So this formula just indicates that in the case where k is a constant, then we are able to exactly solve the gradient descent dynamics, which will exactly give you the prediction on how the algorithm will perform. And it was like an exponentially efficient solution, which is good. However, in general, this quantity k, so-called QNTK, is actually not a constant. So in general, you can try to derive a formula of it, and then you could already say that it's a function of the training variable theta, and then it's of course in general not a constant, and in fact could be highly fluctuating in the variational angles. So this is a term that we call representation learning, that I will briefly explain this term if I have time later. But in general, the point is that this quantity is just something changing, and in general, that making the solution to be not very easy to solve in general, and it may not have the closed form formulas. However, so what we could do is that we could maybe starting on some limits where k is some approximate constant, and then we are able to try to approximate them. So using perturbation theory and maybe expand it order by order around the regime where k is a constant, and then in order to solve the full gradient descent dynamics. So that is basically the point of part of my talk today. So where we call it an analytic theory of quantum machine learning, so which is similar to perturbation theory in quantum mechanics. So as I mentioned before, so in order to stay around some constant value of k, so one idea is that if your variational angle theta was almost does not change, which maybe it will happen around the end of training, where you does not update your variational angle, so it's called so-called lazy training. And of course, the k is approximately constant. And around that regime, actually, you can try to do perturbation theory. And for instance, here it is the results that shows the leading order perturbation theory, where you can assume that eta is you can do order by order expansion of the learning rate eta, and then as a first order, the solution is t, which is linear relation times an exponential decay factor something towards t-1 exponent, and which is a little slower than a direct exponential decay, but it will still vanish. So that is the correction to the free solution, which is purely exponential decay. So that is an example of the solution of the perturbation theory, and you can in fact do this kind of analysis order by order and around that laser training regime. So that is one of the relatively trivial example that actually you can have some control, and for instance around your end of training as a lazy regime, where you can exactly predict the gradient descent dynamics, which is exponential decay. So this is one perspective of the story, but until now the story is not that different comparing quantum to classical. However, in order to introduce some quantumness, right now I will use some quantum theory about quantum randomness to discuss some statistics behavior of a neurotiny kernel with respect to variational ansatz. So the idea is that we could assume that we are randomly choosing the initial variational angle, so which will make some generic variational ansatz to be approximate K-design. So K-design is actually an approximation of the uniform random distribution on the unitary group. So K-design, where the number K just means that you are predicting your statistics comparing to exact uniform randomness on the unitary group up to kth moment. So that is the definition of the K-design theory, so which is inspired by quantum cryptography and actually black hole physics originally. And then if you are curious, you can read some review papers in the subject. But this is something very important for many basic application of quantum information theory, for instance, quantum cryptography. If you make some assumption about K-design, which is a random selection, uniform distribution of this of the variational ansatz, and then you can actually try to compute the average and the standard deviation of this exponent K. And then what you will find is this closed form formula for the ansatz that I showed before. You can averaging over some uniform distribution of those variational angle theta, and then you are able to have an exact prediction and of this K bar, which is average, that's proportional to L, so which is the number of training variables, and the inverse proportional to n squared, which is a dimensional Hilbert space square, so times trace of O squared. So that means that this average can be predicted, and also the standard deviation can be predicted as well. It is the square root L divided by n squared times a similar factor. So, and what we could learn from this calculation is that firstly, delta K divided by K bar, and which is suppressed by 1 over square root of L. So so which means that if L is large enough, namely the number of trainable angles is much larger than 1, then delta K comparing to K bar is almost 0. So that means that if you randomly choose a variational angle, then K bar is almost a constant. It will be off that much comparing to this number K bar, which is predicted here. So that will give you the situation that for deep random neural network, where here deep means that L is large enough, and then it will automatically be in the lazy phase, and then it will be so many training parameters L, such that if you randomly starting at a point, it will be sufficiently close to some local minima that will try to minimize your loss function. So that is the definition so of the theory, and you could find that it actually works, that it gives a prediction that K bar is the most constant with a small amount of variance. And this will potentially make the theory useful, and also tells us in some deep neural network regime where quantum neural network, it can indeed have the guaranteed exponential decay performance. However, you could already notice that there is potentially a drawback of the theory, which is that n is a dimensional Hilbert space, so which is supposed to be large. And if you consider O as an Pauli operator, then O squared trace is also n. So, and then this expression is proportional to L divided by n. So where if L is much, much smaller than n, which is some cases, if you don't have that many training parameters, if you scale the dimensional Hilbert space, then this quantity will be exponentially small. So however, if you are, so that means that you cannot visualize this k-bar in experiment unless you are waiting for exponential long enough time, and then you will observe this decay. However, actually, one of our recent work, which is in progress, we find that this issue will be kind of fixed in the analog system. Just now, I was showing that this was for layered superconducting qubit kind of variational answers. But if you're working on some answers like the analog system, like the QAOA, so this factor 1 over n squared will be reduced by 1 over n for some technical reason. But this was something very much in progress. But I was just telling that this issue about 1 over n, like subtraction, might be potentially resolved. So in some situations. Okay. So furthermore, so I will talk about how to upgrade the theory from optimization to machine learning, which is that in the general machine learning cases where you will have supervised data x of delta, which is might be classical, might be quantum, and you can encode it into some quantum states. You take the expectation values over that quantum data. You can, on some training set, similarly define quadratic laws, and then you can perform the same calculation. But in general, this k, the QNTK, will become a positive semi-definite and symmetric matrix instead of a single non-negative number. So this is why it is called a kernel, because it's a positive definite and a symmetric matrix. So this is the in general case that for the learning problem, the supervised learning problem, and we find the same scheme will work. The answer will be similar to before, but it was just uplifting from a scalar case to the matrix case, where you actually have a matrix version of the exponential decay of the residual training error carrying some indices, and the algebra will be a little more constant. Where if you are doing the perturbation theory, in this case, you have to introduce so-called quantum meta-kernel, which is a second-order derivative of the residual training error instead of the first-order derivative. That's why it's called the meta-kernel. But those calculations are a little hard, so I will leave this for a curious audience. If you are looking at my paper, you will find some of the related knowledge. But the basic principle of this learning case was the same as almost the same as a warming up example, where you actually have a similar exponential decay, and in some case with sufficiently large amount of training parameters, and then you will get almost a fixed QNTK, and that's a story that for the learning case. And furthermore, I will show some simulations that we have in some real quantum devices, where in the past we did some small-scale experiments to demonstrate the theory, which is a 3-qubit classification problem done in IBM Bogota machine. And then we have studying the neural tangent kernel eigenvalues. And in the lazy phase, where we find that indeed around the end of training, those kernel eigenvalues will be fixed almost as a constant, and then you can see that even if it's noisy, you can still in some degree find it's a constant asymptotically, and trying to match the theoretical prediction, which is this dashed line in this plots, which is a simple experiment that we have done in the past. And furthermore, so we have done as well the verification of the neural tangent kernel scaling, where just now I was already mentioning that for the deep quantum neural network, and then you already have the prediction, and we have this numerical verification that in some answers, that variational answers that we have, and the neural tiny kernel k bar expectation value was scaling as linearly with the training parameter L, and then the delta k divided by k bar, which is a relative standard deviation, was scaling as 1 over square root L. So those could be verified in the real experiment. And also, we find that the theory actually works quite well in the case where you have relatively large L, where those two plots are some instances of the experiment that we have, where actually it's taking a log of the residual training error. So this looks linear, which indicates that it's going to be an exponential decay. And actually, if we read the quantum neural tiny kernel, you will find that they are indeed almost constant during the evolution in some real training examples. Those examples, I think, are noiseless examples with 4 qubits, but you can already see that those quantum neural tiny kernel eigenvalue are almost frozen, and also we can trying to also changing the variational angle and trying to find the histogram of the quantum neural tiny kernel with some probability distribution, and the expectation value and the standard deviation will match the theoretical prediction that I was mentioning before. So this is some like experiment that we have done in this part. And furthermore, I want to briefly mention that we also study analytically about how, and also numerically about how noise could help some kind of variational tasks in quantum machine learning and classical machine learning. So actually, in general, so we know that actually in classical machine learning, we don't have to do the high precision calculation, because actually in many cases, noise actually helps us to perform better. So in one of the most popular algorithms for classical machine learning was called the stochastic gradient descent, where the stochastics was that people even manually add noise to the algorithm, and which is a Gaussian distribution number, and then you include that in the gradient descent dynamics, and you will find that actually the results will perform better. So the reason is part of the reason is because so-called settle point avoidance. So the reason is that because it has noise, so it will like fluctuate in the middle, and that will help you to avoid sticking on the same like settle point of the loss function landscape and not jumping outside, but adding a few noise will help you jump outside and avoid the settle point. So actually we did an experiment in some 6 qubit and 7 qubit example, and it shows that actually if you add noise, and which are actually the quantum noise, and that will actually be better than the noiseless case in the same situation. Where here, this is a real quantum experiment where we show that in fact, the performance is actually better in with the quantum noises cases, and comparing to the noiseless case. That will already tell us maybe quantum noise and in the machine that could help some cases for the performance of a quantum machine learning algorithm. So that was a little like different from what we have. What we know before. So previously, we always want to do quantum error correction, but I'm telling that considering that quantum error correction in some cases is hard, in certain situations, it may not be exactly needed in order to achieve optimal performance. Of course, we could manually add noise, add them back, and on the answer of the quantum error correction. But because it has some extra overhead at the current hardware technology, so maybe in the near term, we can try to avoid it. And this kind of noise will even help you for the quantum machine learning algorithms. So actually, we have some analytic guarantee on why and when it will work. So with some state-of-the-art knowledge from classical machine learning theory, where we borrow it to quantum and find it actually works. And we also demonstrate our theory in the actual like numerical and real experiments. So that is a section where we are almost finishing for the part of the near-term algorithms. Do you have any questions, actually?
No, I don't see any questions. So
okay, great.
Yeah, let's just continue. Can you wrap up the next section in 20 minutes?
Yeah, so sure, it will be wrapped up pretty soon.
Okay.
Actually, I make the later part to be relatively in a smaller scale. So which is about fault-tolerant quantum computing, where we are going to discuss something, assuming that we have a good enough fault-tolerant machine, where we are able to perform large-scale, precise quantum computation. It is based on some ongoing work together with a team from University of Chicago with Professor Lian Zhang, and also together with some other faculties, including Yuri Alexeyev from Argonne Lab, and also Jens Azad from the Free University of Berlin. So the idea is that firstly, in the area of quantum algorithms, there is one particularly important one, which is so-called HHL. So it's an algorithm for solving sparse matrix inversion, which is which is an exponential improvement over the metric size A, compare of the metric size A, where we are going to invert, and which could outperform all the known classical algorithms. So for sparse matrix inversion problems, so this is called the HHL algorithm for linear algebra, quantum linear algebra, which is one of the principal paradigm of designing some quantum machine learning applications. And it requires firstly sparsity, and also it requires matrix inversion on large scale. And we find that so those features might be suitable for some actual gradient descent type calculation in classical machine learning, where we could adapt this algorithm as an important subroutine. So the idea is from the following observation. So recently, there are some people, including Andrew Charles et al., and together with his colleagues. So they find that actually there exists some efficient quantum algorithm for nonlinear differential equations, nonlinear ODEs. So the idea of those kind of efficient quantum algorithms that could potentially outperform classical is because people find that ODEs, nonlinear ODEs, could be linearized. So we know that linearized ODEs, which are basically linear equations, could be solved by this HHL algorithm, matrix inversion, which has exponential enhancement over classical counterparts. So the technique for the linearization is so-called Kalman linearization, used in dynamical systems, that will ensure that dissipative systems will actually have a good control in this linearization procedure. So which means that if the system is dissipative, it's a dissipative nonlinear differential equations, then the linearization error is small and controllable. So then a dissipative system that could efficiently be linearized, and you could use HHL algorithm to solve it. So that combination will lead to an exponential advantage in solving some ODEs under certain conditions. And furthermore, we find that dissipation is an important ingredient in the quantum ODE solver, but we find that machine learning itself might be dissipative as well. Here I have listed a few reasons, which might be like a heuristic. But there are a few reasons that tells that machine learning process, the learning process, is a dissipative process. So for instance, you could find that gradient descent dynamics itself is a dissipative process that cannot be described by a closed system if you understand that in terms of Lagrange dynamics. And also there are like other reasons, and from biology to physics and to activation functions in machine learning. But roughly speaking, the situation is that brain needs to actually forget things in order to remember things. So then that process was hard to invert that happens in our brain, that actually when we are trying to learn, that process itself is highly dissipative. So more concretely, the following is our finding. So this technique that I mentioned about linearization is that towards ordinary differential equation, ODE, could be generalized to ordinary difference equations, where difference equations is a finite difference, and the stochastic gradient descent process itself is exactly a set of nonlinear coupled ordinary difference equations, where actually potentially we can use some quantum algorithms to solve it. Furthermore, in the actual generic learning procedure, and the Hessian eigenvalue of the loss function will characterize the stress of dissipation. In our learning process, at the beginning of the training, actually we find that the Hessian eigenvalues will be much more positive, and they are positive more eigenvalues than negative, and at the beginning of the training process. And that means that the system is highly dissipative and it was learning. But around the end of learning, because we are almost not learning things, and so there are roughly a comparable number of positive eigenvalues comparing to negative eigenvalues in the actual learning process. So that means that the system is not that dissipative. That means that, so actually, for a given learning process, we could take a few earlier steps or even a large number of earlier steps. We know that it's highly dissipative, so we could upload it into a quantum computer, and then we can use HHL solver and to solve it, treating it as an ODE. And then later we can download the result through some tomography techniques and keep running classical learning. And in that case, we are able to receive some possible quantum advantage as a early phase of learning, so which might be potentially very helpful for classical given arbitrary stochastic gradient descent process. So that's the hope. The basic logic for an algorithm that's underlying could be summarized heuristically as, because HHL could solve the matrix inversion, it also could solve the matrix in multiplication. And by some tricks, we are doing like a matrix multiplication during gradient descent actually, and then we solve it using HHL. So furthermore, this algorithm itself will avoid some multiple uploading and downloading between classical and quantum devices, because actually the algorithm only requires you to solve it immediately from the iteration 0 to iteration t at once. You don't need to do it t times. It's going to be done for 1 times, basically by doing matrix implementations a to the t directly using the quantum algorithm.
Sorry.
So
a quick question just to clarify. So
yes.
Am I understanding correctly that with this, you still have a hybrid classical quantum algorithm, but you need to call the classical side significantly less? And so you have less communication, you require less communication between the quantum and the classical side.
Right, exactly. So I will comment briefly about this later, how the communication could be realized.
Okay, excellent.
Thank you. And potentially we will see that maybe this is actually the future usage of quantum machine learning or quantum computer even, because this is really one of the biggest problem in classical machine learning community, is that people are using too many like training parameters. And for instance, right now, maybe you have heard of this ChatGPT, and which is originating from GPT-3, a language model, and it's actually highly over-parameterized. It has 100 billion parameters. If you could take a log on the training parameters, and it's going to be save a significant amount of time. So maybe this is one of the future most important applications of the quantum fault-tolerant quantum computers. So potentially, and you can apply this kind of algorithms to the so-called large language model, which might be very promising, and then maybe so it's going to be very useful and save a significant amount of computational time if you are trying to use some algorithm to solve it quantumly. However, so just now I was mentioned that this kind of experiment will require uploading and downloading, where you only have to do it at once. However, so you still have to upload and download. But for what we find is that actually there is a community, so-called sparse training in the classical machine learning community, that kind of related to this techniques. They are studying how to prune a classical neural network to a smaller amount, which will make the downloading and uploading to be easier. So the uploading is probably fine if you assume the existence of quantum random access memory. So which is a machine that people feel that they could load like a number of n data using logarithmic time. So this is the machine that many people believe it exists, but it's not yet being realized. So because people receive challenge in the hardware, but eventually maybe we will have this kind of quantum memory, but our algorithm is not completely relying on it. If you does not have it, it's fine, but you have to do some pruning technology to firstly trying to prune your neural network, basically by saying some weights and basically they are like vectors you need to load inside into the quantum computer. You have to set some of the components of them to be 0. So this can be done, and in the classical side, and even if you cannot it will capture some features of the original neural network if you use some rules to prune them. And after you do the pruning, you could efficiently upload it to a quantum computer. And in the downloading process, if your state itself is sparse, and then you are able to download it efficiently using polynomial time. So that is some pure state tomography technology that people discovered, not us, but many smart people are working in those areas. And maybe you can look at our upcoming paper. But as a summary is that we are very carefully in order to think about how to download and upload those weights and bias we use to train in the quantum devices using HHL. And we're actually trying to identify some AI model up to 100 million parameters, which is relatively huge for a vision model, because we are actually using a computational vision model, not the language model, because 100 million is the maximum amount of parameter we are able to do based on our computational resource. And actually we are not doing a quantum experiment, but instead we are doing classical calculations that show that which part of the learning process is dissipative, which in our analysis, we find that in the early stage of the learning, it's indeed the model is very dissipative, and then you're able to receive a quantum enhancement. And after some certain time, you can stop the learning and try to download the data to the classical computer and keep running. So this kind of hybrid approach will both utilize the feature of quantum classical, and at least for the part where you have possible quantum advantage, it's going to be like the exponential advantage and exponential enhancement. And comparing to its non-classical algorithms, it's going to outperform comparing to for the point will be logarithmic in the model size. So this is basically the pipeline of the algorithm, and we indeed did some benchmark about our theory together with the theory where we have the proof that how the theory will work, and with the guaranteed performance for stochastic gradient descent. So, okay, so I'm almost running at the end. So for the final comments is that quantum machine learning is a very promising area, and potentially quantum devices might be very useful for large-scale classical machine learning problems. The take-home message is that in the near term, variational algorithms are primary algorithms for running in the NISQ device with noise, and the theoretical tools like quantum neural network kernel are very helpful to design those devices using first principle. On the other hand, machine learning algorithms are sometimes robust against the noise itself. So in the NISQ devices, noise might actually even help us avoid instead points and improve the performance. So on the other hand, in the long term, HHL, the sparse matrix inversion algorithm, is one of the main ingredients of quantum machine learning. We design an end-to-end HHL application for sparse and dissipated machine learning problems, and show that there are some potential exponential gain in this process comparing to all known classical algorithms, which could potentially be universal, robust, generic, and provable. Finally, and from this journey, we know that knowledge from theoretical fundamental physics, where I know that some of you maybe are high-energy physicists, and we find that many knowledge from high-energy physics or theoretical fundamental physics are very helpful for quantum algorithm designs, for instance, including quantum chaos and even related to black hole physics, and also dissipation process that we have utilized those are like the very useful concepts and ideas if you are going to design quantum algorithms. Many physics insights are important. So those are like the technical message. I have some other related works that maybe I still have a few time to mention, where we have a work also along similar lines, but so-called quantum data center, which is a combination of the QRAM, the quantum memory as mentioned, together with quantum network, which is not exactly related to this work, but it's something like also I have in mind about understanding how quantum computing and quantum technology could help data science. And also I have some other works along the similar lines where using symmetries were so-called equivariant neural networks, so which is as a neural network respecting symmetries and to enhance the performance in some problems that's related to symmetries, where I have some works and also ongoing works with collaborators. And also I have some other works about doing quantum machine learning in the analog devices, where we find that quantum kernel method and could be enhanced by some kernel nonlinearity in circuit QED, which is a technique from quantum optics that people, and we are working together with people in the lab and finding that this kind of features for multimode photons might be very helpful for some machine learning tasks, where we have some work along this line too. And this is actually another direction of my work, also related to artificial intelligence, but it's a startup that's founded by me, and I'm making a small advertisement, and I'm happy to chat together more with some of you if you are interested. It's a startup about key management system for Web3 and blockchains using some enhanced data security techniques, including so-called post-quantum cryptography, which will make your algorithms to be safe against the quantum computers or future quantum attacks. Together with AI techniques, we are able to make some products that are safe for some potential comprehensive attacks. It's a little related to quantum, where actually we are collaborating with people in quantum cryptography and the quantum networks on some of our applications. So I'm making a small advertisement. Maybe it's not exactly related, but I'm happy to talk further on any of those works and also the ideas in our primary talk and also beyond. So I'm running at the end. So thank you very much for your attendance, and feel free to ask me any questions.
Yes, thank you for this detailed and also this kind of inclusive talk. Any further questions from the audience?
Yeah, I can ask one.
Yeah.
So with this sort of, a lot of the sort of quantum machine learning going on right now, both sort of near future and fault tolerant far future, kind of still relies on this hybrid approach where you do some things classically, some things quantum mechanically, or on a quantum computer versus on a classical computer. And you had kind of hinted at, that sort of learning itself is a dissipative process. And so in some sense, one might expect that whenever you're doing this sort of training, you'll always have to rely on the classical side, which handles dissipation a bit better. Is there some hope of being able to do like a full, quantum machine learning method that is purely quantum and you never have to rely on a classical computer for part of the training? Or do you think it'll always kind of be hybrid and that's in fact the most efficient approach?
I think a hybrid might be better because and in many cases of machine learning, actually, it was like a complicated process that contained many subroutines. And then
Yeah. Yeah.
Probably, yeah, because also Harry's
No, Harry's moved.
Henry, Henry is still there, but our speaker somehow.
Should I turn off my video?
No, it's not wrong. It's not wrong.
Sorry. That's the problem.
We can also just.
The speaker, yeah, let's stop recording.